Hello everyone, from wherever you may be. Welcome to the GSE UK Virtual Conference 2020. Some of you may know me already. I'm David Austin and I'm a Senior Technical Consultant with BMC Mainframe Services, primarily working on ZVM and Linux on Z and amongst other things. If you have any questions, can you put them in through the chat window? And I'll now hand over to your presenter, Malcolm Beattie of IBM, who will take you through practical experiences of OpenShift. Thank you.
Thanks, Dave. Right. So welcome everybody. Yes, this really is live, not recorded. It's a virtual event, and rather than get everybody on the microphones, we're only taking questions in the chat. And I know it always seems a bit of a pain to type things in the chat, but please do so, and Dave will read them out to me and we'll try and make it a bit interactive. And I'm happy to take questions or comments or whatever all the way through, as for all of my things, and we'll do some at the end as well. So whenever you like. So yeah, my name's Malcolm Beattie. I don't know who's in the audience, so I don't know how many of you know me and how many of you don't. I work for IBM UK Systems Lab Services, and I'm going to be talking about OpenShift on Z. And we'll see how it goes. There are other sessions in this in GSE on sort of overviews of OpenShift. So rather than do that, I'm going to concentrate on some sort of practicalities, some things I came across, and a few topics that you might be interested in. So let's go ahead. Oh yeah, so I'm Malcolm Beattie. I work for IBM UK Systems Lab Services. So really what that means is I do Z stuff, mostly Linux and ZVM, and that's all the way from consultancy, solution design, technical hands-on implementation, everything basically. Okay, so this is what I've come up with to talk about today. So I'm going to start with the Z-specific differences for OpenShift. So an awful lot of OpenShift is common to all platforms. It's one of its strengths. But there are a few differences for Z, getting fewer as time goes by. So I'll just cover a few of those. Talk a bit about capacity planning. So if you're interested in, okay, how much resources does it take? What do I need to sort out? What do I need to plan? Then a little bit about that. Then one of the slight restrictions at the moment is on the variety of different ways that you can have persistent volumes, that you can make persistent storage available to the cluster. So I'll go into that a little bit. Another thing is when you try and want to make a configuration change to a node and find you're not supposed to do that in the way that you'd expect, how do you do that in the new world of OpenShift? So a little bit of going through how to do that. And then troubleshooting, how to log into a node in various ways. When you're doing things in practice, it's often useful to sort of copy files to and from the place. Although when you deploy applications, in theory, you just deploy them and they, and they work. In practice, when you're using a cluster, quite often you want to do things interactively and try things out. So I'll go on to how you can do that. And then I'll go into a few example images, distributions and languages and things like that you can use. And I will fix my typos afterwards. And then finish with a few open source images and bits of software which make it really easy to do interesting stuff and powerful stuff on the cluster in the event that your organization isn't completely banned from getting at some of that stuff. And then questions at the end, but as I say, if you want to ask questions during the session, then that's fine too. So Z-specific differences. Well, they now released pretty much the same time as Intel on Power. So started on Z with the 4.2 tech preview last December. That's when I first got it up and running on one of my systems. And soon after it went GA, and that was, as you can see, it was a few months after 4.2 had arrived on x86. By the time 4.5 came along, we were only 1 month behind, and now as of late October, 4.6 is there on Z and Intel and probably Power, and we should really stay caught up now. It's not one of these things where we will forever be behind the curve. And there aren't many differences and restrictions for Z and for Power. I'll mostly be talking about Z, of course, but you know, be aware that a lot of these comparable statements are the same for Power as well. And there aren't many differences or restrictions. There are still a few, but again, we should be caught up in a while and then stay that way. So release notes for 4.6 that came out late October sort of document what the restrictions are. And there are a few more than I've put down here, but I'm going to go through the ones that I think are more likely to be important and of interest. And each release of OpenShift that comes out tends to introduce new technology preview features. And then after a while, if it turns out that people like them and they're good, then they become GA. And some technology preview features that arrived in the Intel world and not in Z yet are these CSI volume snapshots and OpenShift pipelines. So CSI, the container storage interface, this is the way that most things now present persistent volumes, persistent storage. And although most containers still use them as a file system, there's relatively new ways of using those now as raw volumes. And because they can use them as raw volumes, there's then a need to do fancy things to them like snapshot them and clone them. And as you'd expect in the earlier days of these technologies, as a technology preview, that's come along and it's come along at Intel and it hasn't quite hit Z yet. The other one there, OpenShift pipelines. So OpenShift pipelines is a derivation of what was known as Tecton pipelines. And Tecton pipelines are kind of, if you're familiar with Jenkins for CI/CD, continuous integration, continuous development, the idea is that you can test things, push things through, build and test and deploy and try things out in various stages and so on. Jenkins was a big hit in the Java world, and it does things in a way that can be generalized a bit, but tends to fit well with Java development. With Kubernetes and OpenShift, really you want a lot of these things to be built into the cluster itself, so the cluster understands the concepts of tasks and steps and decisions and so on. And that's what Tecton pipelines and its derivation OpenShift pipelines is. So I think that's a really good thing, but it's not quite there on Z yet, so I'm looking out for when it will be, hopefully soon now. OpenShift features that are unsupported and that I think are maybe wanted and hence are worth noting here. Multus is the container network interface plugin. So in the same way that CSI for storage allows all sorts of different storage mechanisms to be plugged into OpenShift, CNI is a similar one for network interfaces, not physical network interfaces, different ways of doing networking. What we'll see later is that Multus is quite a nice way of having multiple ways of doing networking within the cluster. And we'll see later on that that might be quite a nice thing to do in the Z world. So I'm keeping track of the fact that it's not quite there on Z yet. CSI volume cloning, so another thing to do with this new way of dealing with volumes. NVMe, so you can't quite yet talk directly to the NVMe flashcards in your nice Linux One box. And this slightly, what I think is a misleading statement, persistent storage using fiber channel. And as you'll see on the next chart, you can do fiber channel, so it's a little bit unclear what they mean by that. So more restrictions and some introductions. So it says persistent shared storage must be provisioned using NFS. So the emphasis there is on the shared part. One of the nice things about OCP, OpenShift, and so on, is that when you deploy a workload, it doesn't matter which node of the cluster it goes to. And if you're wanting that to have the same view of storage everywhere, then that storage needs to be shared. And at the moment, as of the current release, you need at least to set up an NFS server so that some basic things can get access to shared storage across the cluster. If you're doing non-shared storage, so if you can schedule pods to particular nodes, or your pods don't need to be popping up all over the place and sharing access across different nodes at the same time, then there's a bunch of different ways to do that. So iSCSI and FC, in other words, fiber channel. So again, it's not clear what they were saying in the other one. And LSO is the local storage operator, and I will come on to that soon. And that, as for all OpenShift storage, can use either DASD or FCP, SCSI fiber channel protocol. Another restriction: worker nodes must run CoreOS, RHCOS, and that means rather than the full-fat traditional RHEL, and that's been the case on Z since the beginning. On other platforms, earlier versions of OpenShift allowed you to use RHEL, and as of OpenShift 4, really everything is and should be on CoreOS so that the cluster can look after it itself. Those other architectures have some, that if you like, some legacy, so there's still needs for allowing RHEL on workers. There's much less so on Z, apart from a couple of special cases. New features that are introduced in 4.6, so on Z, so now persistent storage using iSCSI is there, and persistent storage using local volumes with the local storage operator, and I'll come on to how to do that in a while. And Odoo, so the developers CLI rather than the admin CLI. That's probably of less interest to the people that are going to be managing, running, installing clusters in maybe my audience, but the actual developers can use Odoo. And the thing is, they're more likely to use it from their workstations anyway. So, but it's there on Z now, so that's fine. Okay, so capacity planning. First thing, how many nodes? Okay, so a node is it's a virtual machine. In a while, it might be an LPAR or an SSC node or a KVM virtual machine or various other things like that. But at the moment, with current Z, it's just a virtual machine of ZVM, because that's a supported way of doing it at the moment. It's an instance of the operating system. If you're coming from the ZOS world, then it's like a member of a parallel sysplex. And the default cluster install typically gets you to create 3 master nodes and 2 or maybe more worker nodes. Does that matter? Well, for the master nodes, it absolutely does. It is fundamental to the way that one of the components of OpenShift works, that you need at least 3 master nodes, and also you need an odd number, and also there is very little point for it being more than 5, and often very little point for it being 5. So really 3 master nodes is the most common. And if one of those master nodes goes down, it's fine. That's why there are 3 of them, and the protocol underneath copes with that. If 2 of them down, it's very, very bad news indeed. And you're not just running at 1/3 the speed, you are down, because the underlying protocol that keeps that data like live and quorums and all of that stuff just can't cope with more than half of the master nodes being down. So if a master node goes down, it's important, right? And there is a way of backing up the data, the underlying configuration data there, but if you don't do it, you can't recover. Okay, so you definitely did that backup, didn't you? Splitting out some internal pieces from the worker nodes onto other nodes can be good, and there's 2 reasons for that. And one of those, that is the main reason that, a particularly good reason in the non-Z world, is that for particular parts of the internal workings of the cluster, so these load balancers that are built in, and the image registry, and for all the stuff that gathers performance metrics and logging and things like that, those don't attract license requirements. So if you move those onto a node with its own virtual CPUs, then you're not paying for those virtual CPUs. But there's another good reason to do this on Z, and that's that there's been some good work from the System Test and Benchmark group in Birmingham, and what they found is that if you move most of these things onto separate nodes, even though they're just separate virtual machines using the same underlying physical IFLs, you get much less variability in latency and performance and things like that. Yeah, it's a good thing to do that. So even if you install with 2 worker nodes, when you start looking at productionizing it and scaling it up and so on, one of the things you probably want to look at is moving some of these things onto other infrastructure nodes. And it's not difficult to do that. And yeah, so nodes are just virtual machines. We're used to doing this on Z. We're used to deciding, okay, shall we scale up a bunch of virtual machines horizontally? Shall we scale them up vertically? How are we going to spread them out between LPARs and KEX and things like that? So, you know, we're used to that in the Z world. CPU, okay, OCP is heavyweight. There is no getting away from that. That's because it does a lot for you. So as it comes out of the box, there's over 100 pods, there's over 100 containers running there doing stuff. And they're doing health checks, and they're checking updates, and they're gathering metrics, and they're rotating certificates of the CA that's built in, and they're doing updates and caching and pruning and logging and reconciling. All of these things are what the cluster is doing for you. You don't sort of necessarily see it going on, but it's there, it's doing good stuff, but yes, it's using CPU doing that. So even without any applications running, it's sitting there using 1 to 1.5 IFLs, and that can be fairly shocking for a sort of traditional Z person, especially because if you're not used to what the cluster's doing, you don't know it's doing anything for you. One thing to note is that does not mean that when you put applications on, they're going to be using more CPU. The CPU usage of running in a container and running in a container in OCP is not more than, it's not significantly or really measurably more than it is running it in an ordinary Linux instance. And that's because a container in Linux simply is a process. You know, a process running in a container is a process running in Linux. It's not emulated or virtualized or layered or whatever for what it's actually running. When we come onto some of the resources that the container might use, like networking, we'll see a difference there. But in terms of just running ordinary CPU stuff, that's absolutely fine. So don't assume that just because it's sitting there at idle using CPUs, the workload that you put on is going to take more than you'd expect. Recommended minimum provision for a cluster is 3 IFLs. If you read the the official statements, you know, support statements and recommended statements. So SMT is on. So effectively, you have 6 vCPUs or threads or logical cores, and those are doled out between the nodes running on that KEK or those LPARs that are sharing the 3 IFLs. And you can, you know, share and overcommit or whatever those in all the usual ways you would. You know, you're not dedicating CPUs in any way. However, you do need to give at least 3 vCPUs. Remember SMT's on, okay? So you've got 6 vCPUs for your 3 IFLs. Each of your virtual machines, give it at least 3 vCPUs, and the official minimum is 4, okay? That's nothing to do with consumable capacity. It's because of the way that OCP does its internal accounting. You can read the details there later if you want, but just give it that number of CPUs. It doesn't mean it's going to take more than it needs to, but in order for it to do its accounting and schedule things properly, that's what you want to do. Memory is a bit easier. Official minimum for each master node is 16 gig. If you reduce that somewhat, things don't go wrong. Let's say, for example, you had one with 8 gigabytes. One might imagine that that would work perfectly okay, not in production and so on. It's not the official minimum. Yeah, it's not supported, but there's nothing functionally stopping it until you reduce it all the way down to it, you know, things getting really quite tight. The official minimum for each worker node is 8, and again, that's a decent minimum. things sort of work with a bit less than that, but at some point when you start firing up some of the bigger performance gathering and metric gathering and other things, then you probably want a bit more. You probably want to keep it at 8 or more. And as your workloads scale up, give them more. You might as well give the worker nodes more memory to start with. If you need to scale things onto different nodes, then then you can do as well. Networking is one of the biggies. So why is that? Well, like most microservice environments now, SDN, software-defined networking, is the way that the environments make things transparent to the container sitting on top. And it makes things much, much, much easier. And it really is worthwhile for them to do that. So your pods and services get their own IP addresses that the cluster sorts out for you with its own internal networking. And everything works no matter where the containers are within the instances or cluster or whatever else. But that has some performance overhead. So there's lots of layers of this software-defined networking, and at the moment, some of that overhead can be really quite high. Some of it you can remove completely by getting by rather than using the generic default completely transparent networking, by giving it lower level access to your hardware, your nicely fast Z hardware, but the trade-off might then be that the cluster can't schedule them as flexibly or handle some of the HA stuff for you. So there are trade-offs to be made there. One of the ways to do these multiple networkings nicely is this multi-CNI, which isn't quite there on Z yet, but hopefully it will be soon. And obviously one of the things that is great about Z is the performance, the high throughput, the low latency hardware. So don't make assumptions that just plonking a workload on OCP, on OpenShift, on Z, and measuring it and saying, hang on a minute, isn't the network supposed to be low latency and fast? Well, the underlying networking is, but it might well be that because of this SDN configuration that there's a fair amount of overhead there. And work is ongoing in making that more efficient. And none of this is particularly a statement about Z. It's just the way things currently are. The Open vSwitch that is used for this SDN, they've been concentrating on functionality and efficiency work is ongoing rather than done. Capacity planning for disk. Okay, so general OpenShift stuff, there's two kinds of disk storage. There's ephemeral and there are persistent volumes. So ephemeral is used within pod containers for the file system that gets formed. And the contents vanish when a pod is stopped or started. So for stateless stuff, that's exactly what you want. But that storage, that disk storage comes out of each node's single install disk. The nodes are running Red Hat Core OS. Red Hat Core OS is a cut down version of RHEL, so it doesn't have all the fancy boot time configuration stuff that RHEL has. So one of the trade-offs there is that it just installs on a single disk. If you are on a non-Z platform, then it's far more common just to have some massive commodity disk sitting there, and that hasn't particularly been viewed as a problem. If you're in the Z world, where for traditional DASD stuff, it's more common to divide things up into smaller chunks, then that can be a bit of a surprise. But yeah, you do need to give these nodes a single disk used for ephemeral storage. And on the next chart, I'll come on to some recommendations there. Persistent volumes, so PVs. PVs is terminology in OpenShift and Kubernetes. LVM, the logical volume manager, also has terminology PV for a physical volume, really corresponding to a physical disk. Don't get the two confused. Right? I will try and, there you go, I've mentioned LVM PV. And most of the time when I'm talking about PVs in this OpenShift presentation, I'm talking about OpenShift persistent volumes. Those are what are used to provide persistent disk storage, and those don't come from the install disk of the node. Those come from anywhere that the node can get at that storage. And there's all those different ways that a node can get at storage, and I'll come on to some examples of that in a minute. So here we go on the recommendations for ephemeral disk. RHCOS, Red Hat Core OS, only supports installing onto a single disk device. So if you're using FCP, if you're using SCSI, then you just make the LUN nice and big, and that's fine. If you're using DASD, then no, there is no way of getting by with having a million mod 3s tied together, right? And no, really, you can't get by with mod 9s, and you shouldn't really use a mod 27, and even a mod 54 is smaller than the minimum recommended of 120 gig. So if you haven't yet got your storage people doing EAV, and yes, it's only a command line option to the DS8 CLI, so create an EAV volume and get a big enough volume. If you do that, then the next thing from a performance point of view is you want Hyper PAV, otherwise your IOs to that big volume are not going to be able to be parallelized nicely. So yeah, if you want to do DASD with this for the ephemeral volumes, make them EAV and enable Hyper PAV, and I will come on to in a minute how you enable Hyper PAV in OpenShift. The minimum supported says 120. In practice, I would say, again, if it isn't production, mod 54 is fine. In fact, you can go a bit smaller than that. But if you go too small, then the cluster itself gets really busy trying to tidy up disk space once it gets over about 85% or so. So persistent volumes are usually consumed by workloads as mounted file systems. And it's only recently that this idea of having block volumes and also object volumes has come along. So most workloads and most containers just want to see a file system. And in the OpenShift world, that's a volume rather than thinking of a volume as a raw disk. And there's different ways of, you can have an individual container reach out to the storage itself, but it's rare, it's not recommended. The pod needs to be privileged to do that. So usually what happens is the node gets configured to reach out to the storage. And that can either be because Linux can do it automatically. So NFS is one of the easiest examples of those, or because Linux can be configured with configuration files in /etc to get at that storage. So iSCSI is one example of that, or udev rules to bring DASD devices or SCSI FCP devices online. And in that case, you need to drop those configuration files into the node's file system. How do you do that? It doesn't seem to be as well documented online as it could be, so I'm going to cover that in a few charts in a while. It's done with these things called machineconfig objects. Or rather than have to do that manually, another way, as always in the OpenShift world, is use an operator. Okay, so if you install an operator in the cluster, the operator then just watches the cluster and does things for you. And we'll see an example of that in a bit with a local storage operator. Then when you're creating these PVs, these persistent volumes for your developers and your workload and your DevOps people to consume, you can either manually create those objects, or again, an operator can do that for you in some cases, and that's called dynamic provisioning. So for NFS, here is how you add a persistent volume using NFS. So yes, you need an NFS server. You might already have one off platform, but if not, just configure a Linux guest in your environment as an NFS server. Might be the Bastion host, might be some other guest that you set up. Few subtleties. There's a few different ways of configuring this. Don't mix and match instructions from different places. This set of instructions is one of the ones that's documented, can't remember where. It works. So if you follow it, it works. Don't mix and match with other instructions. So export with root squash. Create a subdirectory for each PV and give it those ownerships. So owned by user root group NFS nobody, and with those permissions, note there with the set gid bit, which for a directory means it's going to inherit those group permissions on the way down. And finally, a couple of things. I've had questions about this before. The capacity value for a PV need bear absolutely no relation to how big the underlying storage is. So I've got there in that YAML on the right hand side that this PV provides storage of 100 gig. if my NFS server actually only had a 10 gig disk, everything would still work. Of course, the user of that PV might get a bit upset if they actually try and put 100 gig in there. So if you like, from a quota point of view and a keeping tracker point of view, then obviously sort of do the right thing there. But there's nothing that says if I've got a 100 gig disk and I divide it into 100 PVs that I can only say 1 gig capacity for each PV. I could say 10 gig and then keep track of that shared storage just like any storage admin would. And finally, another comment there, if you set the storage class name to a particular whatever name you like, then developers and people coming along won't be able to snaffle that PV automatically, and it will wait until you specify a PVC of that storage class name. And it's a way of matching up between, if you like, the storage side and the developer side, if you know one person wants to get at a particular storage volume. So local storage operator only arrived for Z in OCP 4.6. It's there now, thankfully. And rather than you having to go and set up block devices within the node yourself and create PVs from them, the storage operator can do it for you. And as with all operators, the way that it does that is it watches the cluster to see what happens, and it listens out for you creating particular sorts of objects. And the thing that the local storage operator looks out for is you creating an object of type local volume. So when you create one of those and post it to the cluster, that storage operator wakes up, has a look at it, and says, okay, well, what do you want me to do? And it goes through that list of device paths. So the dev VG local vol 1, 2, and 3. And it goes to all the nodes that you've told it to look at. By default, all of them, but you can filter them by labels if you want. And it goes and down into the node, and it makes file systems on them. And it then auto creates PVs for you corresponding to those and makes them available to the cluster. So I've talked a few times about how to needing to configure.
Malcolm,
Yes,
sorry to interrupt. You've got a question.
Yep, sure.
Is using ZHPF a prereq to using DASD storage volumes?
Linux will use high performance PyCon ZHPF automatically. So and as far as I know, any up-to-date storage will actually do HPF. It was, I think, quite a long time ago when storage sort of didn't. So yeah, there's nothing on the Linux side that you need to configure to do that. It will just it will use it. It'll use those TCWs, the transport command words, instead of the CCWs, and it's a kind of a lower latency way, a nicer way of doing it. So you don't have to worry about configuring that anywhere at all. It's really the EAV and the Hyper PAV parts. An EAV is really just a volume creation time decision, because when you try and create it bigger than a mod 54, it sort of does it, kind of. And Hyper PAV is definitely a configuration change you need to meet, and I'm going to cover that in a chart or two. Okay. All right. So Dave, if you come back with any extra questions, if that didn't answer them, then do so. Otherwise, I'll carry on now. Okay. So some of these configuration things, you need to go and add a configuration file to a node. You don't log into the node anymore. Well, not unless you're troubleshooting and you have to, and I'll cover that in a little while. So the node itself isn't running full fat traditional RHEL, it's running Red Hat CoreOS, and the cluster itself installs and manages that node. You don't have to log in and patch it and maintain it and look after it. The cluster does it all for you. And as a result of that, any changes that you make to the file system, if you go in and put something in /etc somewhere, it can easily be lost the next time it does an update. On the other hand, some configuration changes that you need to make do need to drop files into there. And so, when you look onto the, the OpenShift pages and it says, for Z enable Hyper PAV, well, how? Okay, well, here's how. And the answer is that OpenShift in general uses these machine config objects to build the files to place into a Red Hat CoreOS node. Yeah, it sort of does a load and go for most of the data in there, and then on top of that it drops some configuration files, and those are built from these machine config objects. So if you want to drop a file or some files into /etc typically to configure these things, then what you do is you create a machine config object and you give it a label of role node type, role with the URL prefix so that you're not clashing with anybody else, that machine configuration.openshift.io role. And so if you give it a label of role worker, then these files will be dropped into all the worker nodes for you. And the file that you put there, you tell it the path name and you tell it the contents. The contents to put there are taken from a URL. Now, you really don't want to have to faff around putting a configuration file up on a web server somewhere just so the cluster can fetch it. So one of the things you can do with the URL, which doesn't seem to be as widely known as it should, is actually have a URL with inline data. So that the URL scheme there is data colon, and in general it's of the form data colon and then the content type comma and then the data. We don't care about the content type, so you can see here data colon comma and then all the data you want to put in. Now, because it's a URL, if it's binary data, you need to URL encode it and do that however you like. There's an example there with a Perl one-liner, there's Python one-liners and utilities, but however you do it, it's the usual one where you've got the the percent and the 2 hex numbers to encode all of these things. So here's an example. So for Hyper PAV aliases, how do you enable Hyper PAV on a normal Linux instance? Well, you go dev, and what that does for you is brings those devices online and writes a few attributes to them, and also plonks a file into the udev directory so that it happens again at next reboot. Well, if you then take the contents of that udev rules file, so here it's 41 dasd eckd, whatever it says at the bottom there, .rules, take that content, URL encode it, put it into a machine config object, post it to the cluster. Then whenever the cluster is doing anything with the nodes, when it's making any changes, it will automatically render that into the files, put it on the node for you, change everything, reboot the node if it needs to after moving all the workload off, and you've got that configuration file there persisted. Okay, so troubleshooting. One of the first things that people tend to want to do, at least when they're asking me about this, is, okay, I've got the node, I've got a Linux instance there running OpenShift. How do I log into it? And of course, the answer is usually, well, you shouldn't do that. The cluster looks after it for you. And most of the time it does. And whenever it needs to be patched and updated and so on, the cluster will do it for you. It'll move all the workload off. It will make the changes. It'll reboot the node. It'll move the workload back on again. It'll then go to the next node. That's the cluster's job. It does all that for you. But sometimes you want to log in. And the preferred way of doing that these days is with this OC debug command. So if you go OC debug node and tell it the node name, the virtual machine name, what it actually does is it starts up a pod, starts up a container, which it then schedules onto that node. So the node's running a container, but instead of that being a typical pod, which is nicely fenced off from the rest of the world, it's a pod which is given access to the real namespace of the node. And the real file system of the node is then mounted on /host within your container. So, and your container is then connected to your OC client. So obviously OC, as usual, can be running on your workstation, Linux or Mac OS or even Windows. And as all normal, the magic of the networking makes all this work for you. So you go OC debug node on your workstation, and you get a command line prompt on your cluster. That's normally the best way of doing it. If things are really, really broken and the cluster can't even schedule a pod and get that to work, then that might not work. In quick case, the workaround is, okay, you can SSH in. And the way that you SSH in is when you install the cluster, one of the very, very few parameters you choose at configuration time is an SSH key. and that's an SSH private key. Well, the SSH key is the public key for a private key of your choice, and that gets placed onto the nodes and trusts you if you can present that private key. And the main things to remember there are the username is core, not root, not your own username. And if you've given it generated a separate private key identity file at cluster install time rather than just use your normal SSH key, then don't forget to give it the path to that private key rather than your normal one. And finally, when you do SSH into a node, it notices and it marks the cluster to say, oh, somebody SSH'd into that node. That I guess that Red Hat support people if you need to get support from them. If you raise a support issue, they will see, oh, they SSH'd in. Oh, I wonder if they messed anything up. They might ask you about it. It's non-preferred. It's not forbidden. It's just a non-preferred way of logging into the cluster, of logging into a node, the underlying node. Another thing that tends to be quite useful is copying files to and from containers. And again, it's one of these things that I've had a number of people express surprise that you could do this. So I thought I'd put in a chart on that. If you have a running pod there, then you can use OCCP to copy a file from that pod to your workstation or from your workstation up into the pod. Obviously, if you copy a file into a pod and it's in the ephemeral part of the pod, it's not from a mounted persistent volume, then when the pod gets deleted, that goes away. So you can't use this to make permanent changes to an image. That's not the way that you do it, but it is sometimes useful just for copying things in and out. And you can even copy files in and out of an image without needing to start up a container from it. So OC image extract will do that. An image name there is, as always in the OpenShift world, it's just the name of an image, perhaps preceded with a registry. You don't need to download the image as a local file. You just tell it the name of the image, and the cluster will go and get it for you if it doesn't already have it cached, and build it all up for you, extract that, and copy the file out of it. So when you're sort of using things, when the cluster's running in production and people are deploying applications and building them, they're using the cluster sort of the way it should be, and you don't necessarily need to log in interactively to things. In practice, if you're troubleshooting and trying to try things out and you're trying to build some of these, workloads and ways of doing things, you want to try them out interactively. So in order to do that, I mean, the first thing to note is that as a container is running, the logs are available, and they're not just that they're available from the CLI, and they're available from the web console. You click on the pod and go to the tab logs, and those are live. Okay, so one of the really strong things about the OpenShift web console is it's a proper modern reactive web application. In other words, it holds the WebSocket sitting there. It's event driven. So as something gets written, as the container writes a line out, it goes straight to your browser. It's not sitting there spinning and polling. You don't have to click refresh every 5 seconds or 10 seconds. You don't have to wait until the container's finished and download a log file. You are getting immediate live streamed access to those logs. And similarly for terminal access, you can get a direct terminal session within a pod. And what's actually happening there's a shortcut OCRSH, and like remote shell in the old days before SSH took over. It's not actually using the RSH protocol, of course, but what it's actually doing is it's starting up a shell in the namespace of that container. It's connecting it up to your workstation by the OC client and by the connection that it has, and it's giving you a live shell directly within that pod. And you can also do that from the web console as well. And again, it's a live, like terminal emulator session built into the browser, no Java needed, no downloads needed, no install needed. It is direct, live, terminal shell and streamed access within your browser. That won't be a surprise to anybody, developers using IDEs and seeing terminal sheds and using sort of Eclipse Shell or Thea and things like that. It's but for the Z world, having a browser thing you just click, doesn't need to download a hold of Java, and getting live direct access to something is maybe a bit of a change. Also, you can, so that was if you're connecting to an existing pod. Quite often what you might want to do is you have a deployment or a build or a daemon set or stateful set, or all these ways of deploying things in the cluster. And if everything goes ahead and starts up, something goes wrong. And what you want to do is just get in there and try it out and see what's going on. So what OC debug for that kind of resource does is it figures out what kind of pod the resource would have created and just tweaks it a bit, so that instead of running the software with all the options itself, it loads everything up into that container and then starts a shell in it for you. And that's a nice way of debugging things as well. Now, starting an interactive pod from an image. Again, this is really sort of OpenShift 101 stuff. Simply using it to start up a pod, a bit like just using Podman or Docker to start up a container. This is about the most basic thing you can do in OpenShift itself. And that OC run there and tell it an image name to run. That's what OC run does. It fetches the image for you, and in OpenShift by default it knows about keyquay.io, and it knows about Docker.io, so all of those images will be pulled automatically. If you've say installed a Cloud Pack, an IBM Cloud Pack, then part of that installs an operator which puts the IBM Cloud Registry in place. cp.icr.io is where the Cloud Pack images come from. Or you can just give it the name of a registry as a prefix to your image name, and it will go and fetch it from there. And it starts it running, and the -IT tells it to make it interactive, connect it to your terminal and make it look like a terminal. And you can explicitly tell it to run the command bin sh if normally the container would have gone and started its own daemon or whatever it is, provided the image file system has a bin sh. Otherwise, if it's really, really minimal, it gets a bit tricky. So what sort of images can you run? Well, this really is because again, I've had questions from Z folks about, well, this is, OpenShift runs on Red Hat. Oh no, that means I can no longer run my software that wants to run on, my developers want Ubuntu, or I've got something that runs on SUSE or whatever it is. The Red Hat Core OS in this case that's running on the node is simply hosting the containers. One of the points about containers is the thing that's running in the container doesn't need to be the same distribution. The only thing it needs to be is a Linux executable, which uses Linux syscalls for the hardware architecture that it's on. So within your cluster, you can run the UBI8. So UBI is what Red Hat called the universal base image. So that's, if you like, the most cut down RHEL. It's RHEL cut down for running in containers. So it doesn't need to run all of the software for an entire Linux instance. All it needs to do is have enough of RHEL to run what you want. That's what the UBI is. UBI8 is based on RHEL 8. But if I say OC run image equals Ubuntu, it'll go and fetch the official Ubuntu image from Docker Hub, and it'll run you in Ubuntu. If I say run SUSE SLE15, well, registry.suse.com, because they host it on their own registry, then it will pull the official SUSE Linux Enterprise image and run that within your container. And sometimes, yes, OpenShift has all of these facilities for fancy development and so on. And yes, they're really nice. But sometimes you just want to run an image with some software in rather than have to mess around installing it yourself. So just run the image Golang, let's say, and then that has your complete, Go compiler and Go build environment, and then anything which you need to build where because somebody hasn't bothered to publish a Z executable yet, you can just do a Go build on that, get the executable, copy it out of the image, and there you go. There's plenty of open source software and proprietary software that does interesting stuff, and a lot builds on Z already. If you go and have a look on Docker Hub now, then the way that these manifests work, more and more things are getting automatically built for multiple architectures. You don't need to know that. You just tell it the image name you want, and if you're running on Z, it'll pull down the Z version. If you're running on Intel, it'll pull down the Intel version. Most of the time, it's exactly the same image name. Cases for things like Clefos, the Cinnamomene provided rebuild of CentOS, has a different name at the moment. So yes, you need to tell it to use the image name Clefos instead of CentOS. But if you really want to hide those details, then OCP has a thing called image streams, and you can sort of set up aliases for that as well to hide any naming problems. So finally, I thought I'd go through some interesting open source images. Most of the time for Z customers, there's two reasons for sort of bringing up OpenShift. The main idea is you're going to want to run some business application on that, and some of the time that's ready to go, and the developers provide you with your jar file, and you pop it into a Spring Boot image, and everything springs to life, and everything works nicely, and everybody's happy. Some of the time, though, they go, okay, well, we've got this OpenShift cluster installed. I want to see it do something. And unless you're completely, if at all you can get access to, these bits of open source images on Docker Hub, then and GitHub, then they make really powerful examples of demonstrating useful stuff. So one of the ones that I like is Gitty. So this is for hosting Git repositories. So if you think of things like GitLab, GitHub, and Bitbucket, they're not only running Git repos, they give you a nice web access to them. So rather than have to go and tell everybody to, install Git and check in, pull and push things that way, you can point your browser at it and go and create a repo. You can go and browse it, clone it, look at the documentation, create users on it, and so on. Gitty does that for you very easily. Fire it up, runs within your cluster, and your cluster itself can use that if you're needing to fetch and push things from a Git repository, which a lot of builds want to do. RabbitMQ is a nice, easy message broker to get things going with. Lots of different protocols, lots of different bits of utilities. And the nice thing for getting started is it's got a nice web interface. So you just point your web browser at it, and you can go and create queues, look at queues, browse things, test things out, pull and push things, and so on. Node-RED is a low-code programming for event-driven applications. Again, it's Node.js under the covers. It has lots of ways of getting data in and out, but importantly, you just point your browser at it, and you drag and drop within your browser various different nodes and inputs, and drag lines between them, and so it's really a very easy way of getting something going, again, without having to install lots of stuff on people's workstations. MinIO serves up S3 compatible storage. So one of the things about a lot of cloud stuff is that you an awful lot of things use S3 object protocol, and trying to get your company to give you access out to real AWS or real IBM cloud might take a while. Install MinIO in your cluster, and you can go and push and pull objects from there, and it's got a nice little web interface so that you can upload and download objects directly from your browser as well. And finally, Benthos, which I only came across 6 months ago or or so. I really quite like it. It strikes me as a cross between CMS pipelines, and I've seen ZOS folks use DF sort for all sorts of filtering things. Those of you that follow IBM Main have seen the amazing things that it can do. And that's not for its fundamental sort of sorting and merging. It's simply that it can take data in, it can read fields and filter them out and munge them and write them to some output. And in order to do so, you just run the single program df sort and you give it a single configuration file, if you like. Benthos is kind of like that, but the inputs and the outputs are coming from anything cloudy or even anything local. So multiple files, tar, CSV, messages, S3 objects, all the things are put there. Bring them in, you give it a configuration file, it can then process them, filter them. The way that it filters things is very powerful. It can do JSON and XML and all sorts of things as well. It's got an optimized language for you to do a lot of that filtering for you. And it does a lot of the stuff for you, like parallelism and throttling and streaming, and shows you metrics as things are going on. Yes, I rather like that. So finally, are there any questions? Dave, anybody been putting anything in the chat?
I think everybody's been very shy this session.
Yeah,
only the one question you've already had.
Okay, it is difficult, putting stuff in chat rather than just asking. I've found that myself with a lot of these virtual things. Okay, in which case I shall say thank you for listening. Thank you for attending, everybody. And Dave, if there's nothing else, I think we shall close it.
Yeah, okay. Thank you all for attending. I look forward to you at any future session.
Right. Thank you then.
Don't forget the feedback, please.
Oh yeah. Oh yeah. Sorry. Let me put that onto the. Yes. Please submit your session feedback. There you go. I've forgotten that. There we go.